Arnab Bhattacharyya from the National University of Singapore, talking about efficient distance estimation and causal inference for discrete models. Thank you, Arnab.
Okay, thank you. And thank you for being here early in the morning. And thank you to the organizers for this great workshop. So I'm going to talk about efficient algorithms for estimating distance between Bayesian networks and for learning post-interventional distributions in causal models. This is joint work with a bunch of people who I'll mention during the talk. Okay. So let me just kind of do a bit of setup. So suppose you're a cancer researcher, right? And you are measuring biomarkers for various kind of biomarkers. So you have hormone levels, gene expression levels, presence or absence of antibodies, other growth factors, and markers indicating presence of tumors. And you have many of these markers. Okay, so you can measure many of them. I mean, and throughout the talk will denote the number of variables or the dimension of the data. And you observe these samples for several individuals, right? And the goal after you obtain this data is to answer statistical or causal queries. So statistical queries would be like you would be asking about the joint distribution on some subset of variables. Causal queries would ask, I mean, what would happen if you administer a treatment that affects a few of these variables and you ask about the effect on some other variable, right? And the way we typically model this is that we think of these as n random variables. And these variables are, of course, I mean, the whole point is that these are not independent. They are products of some grand physical process. And the idea of causal inference is to learn properties about this underlying generative process. Okay. So how do we model this process which is generating these variables? So we kind of go back to Laplace in the 1800s, who thought, I mean, who kind of envisioned a deterministic evolution of the universe. So the universe kind of is an effect of its past and determines its future. So this is kind of the way that we'll model the generation of variables. So you have this one, yeah. So each variable is a deterministic function of its parent set of variables. This is a subset of the variables, and some other set of variables that are unmeasured, that you don't know. So the stochasticity in the evolution comes from the fact that these UIs are unknown latent variables that are not measured, but we'll think of these functions as being deterministic. Okay, and the way often that we'll depict this causal model is by a causal diagram, where you have variables as nodes. You have edges from parents to children, and if there's no dashed arc between two variables, like between x1 and x2 and x2 and x4, the corresponding UIs, the randomness, we'll think of as independent. But if there is an arc, then the randomness is dependent. So without loss of generality, we can take u2 to be equal to u3, and this is what's known as confounding. So x2 and x3 are confounded, right? Right. So throughout, we'll assume that this causal diagram is acyclic. So which means that that there's a linear ordering in which the variables are being generated one after the other, and if there's no confounding, so if there are these no dashed arcs, then basically this just corresponds to a standard Bayesian network, where you have each node, there's a conditional distribution of the node given its parents, and then that completely determines the whole system. And also, I mean, this way of writing it explicitly specifies the effects of what it would mean to administer a treatment. Okay, so maybe let me just give a very simple example just to make sure that we're all on the same page. So if you have two variables x1 and x2, right, and you have a latent variable u, which is common between x1 and x2, and the functional equation is x1 equal to u and x2 is equal to u xor x1. Okay, and u is just uniform on 0 and 1. Okay, so then the observational distribution, so x2 is 0 with probability 1, right? Because x1 is equal to u, but x2 do x1 equal to 0. So what do x1 equal to 0 is exactly this intervention, where you go in and you specifically set x1 to be equal to a particular value. So if I set x1 equal to 0, so this means that on the right hand side, I change this x1 to 0. So x2 do x1 equal to 0 is basically distributed again uniformly in 0, 1, because x2 becomes equal to u. Okay, so this is the notion of intervention. So it's a completely, I mean, right. So if you write it this way, it explicitly specifies what an intervention means. And so we'll try to make minimal assumptions. So we'll have, so the n, the number of nodes or the dimension of the data, we'll think of as asymptotically growing. And for statistical computational reasons, the goal of this, the work that I'll describe will be to understand to recover the causal model, or to recover the some parameters of the causal model. And so we'll need to assume some sort of sparsity on the model. Okay, so typically we'll assume that the in degree of each node is bounded, which means that each node can be written, the width of this functional equation description, this is bounded. And also we'll assume that the dashed edges have bounded span. So for example, you cannot have some God hidden variable which confounds everything else, because this would mean that you can have an arbitrary distribution on the n variables, and this is not tractable. And finally, we'll work with discrete variables over a finite alphabet, but this assumption can be relaxed, right? But we'll throughout assume just discrete variables, or even if you like, just Boolean variables. Okay. Okay, and finally, throughout the talk, I'll be talking about approximation of probability distributions. And to define approximation, I need some notion of distance between probability distributions. And we'll work with two notions, the total variation or the statistical distance, and KL divergence. I think I'm missing a factor of half here, but it doesn't really matter. So this is, so the total variation distance, you can define it as the L1 norm between the probability mass functions, and the KL divergence has an expectation over P of this log ratio. Okay. And one important thing to notice, at least for the first part of this talk, is that if P and Q denote distributions over the n-dimensional space, computing this TV or KL is not a trivial job, right? This is like a sum over an exponential number of x's. So you cannot do it explicitly using this formula. All right. So TV will be kind of our gold standard for distance in this talk, because if I can say that the total variation distance between two distributions is small, this also implies, for example, the distribution of marginals is also small. If PQ are close, then their marginals are also close in total variation distance. Any event that happens under P also happens with approximately the same probability under Q. So this will be the notion that we'll usually work with. All right, so let's begin. So in the first part of this talk, I'll be talking about algorithms for distance estimation. So just to motivate this, right? So I told you about the functional causal model or Bayesian networks if we don't have confounding. But this is not a unique description, right? So you can have different Bayesian networks which yield the same observable distribution. So this is the Markov equivalence class partitioning of all DAGs on three variables. So basically if you have a distribution that can be expressed as a causal model or a Bayes net on this DAG, then it can also be expressed in this DAG and this DAG, right? So there are different alternative descriptions of distributions in this language. And there's even more ambiguity if we allow the distributions to be approximately equal, not exactly equal. And so the question is, can we test such approximate equivalence efficiently, right? And let me just formulate it in this very crisp way. So so just to kind of hone in on the computational nature of the problem, we'll look at this question. So you have two distributions, P and Q. You have the explicit description of them as Bayes nets, okay? And the question is to compute the total variation distance between these two distributions, okay? Now, of course, in reality, you may be kind of estimating these from samples, but just to understand the computational nature of the problem, let's assume that you have a complete description. Yeah.
So here, if you're given the descriptions of the networks, you can forward sample from them, right?
You can sample from
So why can't you just estimate the L1 sort of by directly sampling from P and then looking at, do you get an unbiased estimator that way, or you're worried about sort of variance?
It's not an expectation, right? It's a sum of.
Okay.
So that's one of the things that we'll discuss. Having unbiased estimators and yeah. But just if you want to compute it exactly, so this is just a purely computational problem. And our first result is that even for product distributions where the graph is completely empty, computing it exactly is a sharply hard problem. So prior to this work, I mean, the only results about statistical distance was a older work by Sahai and Vadan, where they showed that if P and Q are generated by sampleable distribution, so they are outputs of circuits, then this is a hard problem. But this kind of strengthens it to, I mean, even if you have two product distributions, then the total variation distance is hard. Computing the total variation distance is a hard problem. So let me just give you a brief idea of the proof of this, because I mean, it indicates something important. So the way we prove this is that we first look at this problem PMF equals, which is the question. I mean, if you have a product distribution P and some particular value V, you ask for how many x's does P of x is equal to V. Okay. And it's not hard to see that this basically is a generalization of the subset of the counting version of subset sum problem. So subset sum is asking if you have a bunch of numbers, for how many sets is a subset of those numbers equal to, for how many subsets is the sum in that subset equal to some particular target. So asking if P of x is equal to V, you can, so if S denotes the set of, so here, let me just assume, right, so this is these are distributions from 0, 1 to the n. So if S is the set of indices where xi is equal to 1, then P of x is equal to V can be written in this way, which you can easily massage into a subset sum kind of, so you're looking for subsets S where the sum of these quantities is equal to this. So this basically is a direct reduction of subset sum to PMF equals. And so the key part of the reduction is I mean, showing the hardness of this PMF equals problem. So showing that PMF equals reduces to TV computation. And so what we can show is that, so you can, so given a distribution, so you're given a P and Q, right? So, sorry, you're given an instance of PMF equals. So you can come up with distributions P prime, Q prime, P double prime, and Q double prime, which are on a larger number of variables, on n plus 2 variables instead of n variables, so that the number of x's where P of x is equal to V can be expressed as a difference between two total variation distance computations. Okay, and right, so if you have efficient algorithms for total variation distance, then basically it also implies efficient algorithm for this PMF equals problem, which is a hard problem. Okay, yeah, one thing is that because we do this kind of a two-ring reduction where you have a difference, I mean, it doesn't rule out a relative approximation. I mean, it could be that you have you could have like very good approximation of the TV distance, but the difference could be a very bad approximation of the left-hand side, right? So it doesn't rule out approximation, but at least it shows that that exact computation is right. Okay. Yeah.
Do you know if the problem is in Sharpie?
Yeah, it's in Sharpie. Yeah, so it's a Sharpie complete problem. Yeah. Okay. Okay, but in fact, even approximation is hard if you just allow degree 2. Okay, so deciding whether TV of PQ equals 0 or not is NP hard if the degree is allowed to be 2. And this is actually a very simple reduction. I can just quickly show it. So this basically also implies that relative approximation, so multiplicative approximation of TV distance is going to be hard, because if you have a multiplicative approximation, you can distinguish between whether the TV distance is 0 or not 0. And this is just a very simple reduction from circuit SAT. So if you have a circuit, a Boolean circuit, and you're trying to decide whether it's satisfiable or not, so you can reduce it to the TV computation between these two Bayesian networks. Okay, so what we do is just we endow the inputs with the uniform distribution, and the gates in the middle, they are deterministic functions. I mean, the way they usually are. And so we just add an extra node. So in one case, it's the uniform distribution, which is just independent of everything else. The other case, it's an OR between the output gate and a uniform distribution. Okay, So if, for example, this instance was not satisfiable, so x9 was always false, then this x10, I mean, is going to be just uniform. So these two distributions are going to be identical, right? And it's easy to see that if it is satisfiable, then the distance will be non-zero. So so TV of PQ is non-zero if and only if the circuit sat instance is satisfiable. So this tells you that that there is a that, I mean, yeah. So deciding zero versus non-zero is a hard problem. So so just one remark. I mean, it's not possible that, I mean, this TV is zero versus non-zero. Of course, for product distributions, it's actually an easy problem, right? I mean, if you have a product distribution, you just have to check whether the parameters are equal or not. That's the only way that two product distributions can be identical. But once you get to a degree which is at least 2, then you have at least NP hardness. So we don't know the true hardness of the approximation problem, actually. Yeah, but then I think building on Ankur's idea, you can, so additive approximation is possible, okay, and you can do it efficiently. And here's the idea, I mean, which, I mean, you can build an estimator which you can evaluate empirically. So what you do is you look at this L1 norm and you can write it in this way. So you can take out P of X and you can write this sum in this way, okay? And the nice thing is that this estimand is kind of bounded, is between 0 and 1. So you can just easily draw samples from P. And if you have the parameters of these two distributions, P and Q, you can exactly evaluate P of X and Q of X, right? So you can evaluate this for X's that you sample from P, right? And by a standard Chernoff bound, you can estimate the TV up to plus or minus epsilon, okay? And this works not only if you have exact description of P and Q. If you learn P and Q from samples, which I'll describe in the next part of the talk. So if you learn P and Q up to some total variation distance error, okay, and you plug in, so instead of using the exact values of Q and P here, you use Q hat and P hat, which you learn from samples, then also you can show that this is a plus minus epsilon approximation, okay. And this general idea is kind of, okay, by the way, I mean, so the way this testing algorithm works is by actually learning the parameters first, like I said, and then you use that Q hat and P hat for evaluating this estimate. It's still an open question if you can do plus minus distance approximation without actually resorting to learning. Okay. Yeah.
So this is an additive approximation?
Yeah, this is an additive approximation.
I see. What about multiplicative approximation?
Yeah, so I'll talk about that. So multiplicative, we saw that even if the degree becomes at least 2, it becomes a hard problem. But we can still say something about when the degree is less than 2. Right. Yeah, and then this strategy kind of is actually quite general, right? I mean, like this doesn't actually rely on anything about BaseNet. So it's an interesting question. Even if you give me 2 high-dimensional Gaussians and ask me, I mean, you give me the parameters of the Gaussian and you ask me what is the total variation distance. So there's no kind of explicit formula for the total variation distance between 2 Gaussians, but you can use this strategy to get a good additive approximation. Because again, if you have the parameters, you can of the Gaussian, you can evaluate the probability density function, right? And similarly for ferromagnetic Ising models, you can approximate the partition function and you can get an approximation of these Q and P's. Okay, yeah, so the question you all asked is about this relative approximation. I find this a fascinating question. So what we showed is that, I mean, a bit surprisingly, polynomial time approximation algorithm is possible in some cases when you have product distributions. For example, let me just sketch what happens when Q is uniform, right? So suppose you're trying to test you're trying to approximate the distance from an arbitrary product distribution and uniform. So essentially you can reduce this to approximate knapsack counting. Okay, so what happens is that you take the PIs, right? So the PIs are the parameters of the product distribution. So the total variation distance, you can write it in this way. And you can just kind of separate this sum into, I mean, you can ask for how many sets this guy will contribute something in some range, okay? And that basically reduces to approximate knapsack counting. So counting how many sets where this quantity falls in some range is essentially approximate knapsack counting. And you can use now classical algorithm due to Dyer to do this task. Okay. And yeah, and using an idea due to Raghu and co-authors, we can, so where, I mean, they use ideas for read once branching program, I mean, like for sampling from read once branching program. So we can extend this to more general classes of product distribution. Okay. Okay, so any questions about this part? So we still don't have a complete understanding of for what product distributions you have hardness versus where you have a polynomial time approximation scheme. Okay, so let me then go to the second part of the talk, which is about distribution learning. So here, the question is that you're given, well, okay, so let me first say in general what the problem is, right? So you're given, so you will assume that the causal diagram is known. Okay, this is part of the domain knowledge. The causal diagram is known, and you get samples from the observational distribution. Okay, and the goal, I mean, the final goal that we'll look at is being able to generate a description of the interventional distribution. So what happens when I do an intervention on a subset of variables? I'd like to get a description of that interventional distribution. So let's just start very slow and ask what happens just with the observational distribution. So I get observations and I'm trying to learn the observational distribution given the DAG. Okay, this is just fixed structure learning where the structure is known and you're just trying to learn the parameters of the Bayesian network. All right. And yeah, so this is the first case where you have no confounding, right? So here, I mean, this is a well-studied classic question. So it's clear what you do if you have thought about these things, right? I mean, so you take each variable and you try to learn the neighborhood. I mean, so for each variable, you just learn the distribution conditioned on its parents taking on some values. So define pi sigma to be the distribution of xi when the parents of xi have value sigma, and our strategy is to just estimate these distributions pi sigma as qi sigma. Okay? So I just want to pause for a moment to contrast to the talk yesterday, for example, by Raghu, where, I mean, he was trying to learn the graph itself, right? So here the graph is known. So the question is to learn a distribution. Okay. And the guarantee that we want is that the distribution should be close in TV distance to the actual observational distribution, to the true distribution, right? And we would like to understand as a function of the error in approximation, how many samples you need. Okay. Okay. So, right. So we just want to estimate these local distributions, these conditional probability distributions at each node. And there's a very nice fact about Bayesian networks that you can decompose the KL divergence between two Bayesian networks on the same graph. So if P and Q are Bayesian networks on the same graph, then you can write this KL divergence as the sum over the variables of the expectation over the distribution to its parents of, so the sigma is an assignment to the parents of xi, of the KL divergence between pi sigma and qi sigma. Okay. So all that you need to do is to be able to take enough samples to make sure that you estimate the KL divergence for each of the I and sigma to small error, right? I mean, it's not really necessary to estimate each of them, because if some sigma happens with some very small probability, then you can essentially, I mean, unless your KL kind of blows up, we can discard those sigmas which have extremely small probability, and we only look at the sigmas which have sufficiently large probability. Okay, but it is an issue that we don't want KL to become infinity, which it can, right? So we just have to ensure that this stays bounded, and then we need to estimate this pi sigma for those sigmas where the probability of the parents having sigma takes on some significant probability. Okay, so first, just this general question. So if you have two, yeah.
So can you assume that P and Q have the same structure?
Right. So I'm assuming that the graph is known.
Okay, for both of them.
Yeah. So here the graph is known, and you're just trying to learn the description of the distribution.
But I think this decomposition is true independent of the graph. No? It also works if you just decompose P and Q in terms of other conditionals.
Yeah, I think. I mean, so if the parents are different, I think you need.
I think so, but we can talk about it.
Okay, sure. Yeah, I think one of them. Yeah, I mean, there are some extra terms otherwise. I mean, there are some additive terms. I think if one of them is not in this graph. But we can talk about it later. Yeah. Okay. Right. So just like a very simple question. So how do you ensure that Pi sigma and Qi sigma are closed? So these are just distributions. So let's say that all the variables are from 1 through k. So these are just distributions on 1 through k, right? So I just want to learn a distribution on 1 through k so that the KL divergence is small. Okay? So this is a basic question, and actually, I mean, as far as I know, the optimal answer is still not known. So one thing that you can do is you can use what's called the add-1 estimator. So if you get, so if you have a distribution on 1 through k, I can define this add-1 estimator, which is, I mean, basically the empirical distribution, but you add 1 to the count of everything, right? So so the empirical distribution would have been ni over n, where ni is the number of times I appears. So here I do ni plus 1 over n plus k. So I add 1 to the counts of all the possible domain elements. And right, so we showed that there is basically, I mean, you can that you have this high probability result. So if you take sufficiently many samples, then the KL divergence decreases. So if m is the number of samples, then then with probability 1 minus delta, the KL divergence decays at this rate. Yeah, so we actually don't know how to remove these log factors. I think that I mean, for this basic question, that's an interesting problem. Anyway, so you can apply this directly, and yeah, so you can basically, so like I said, I mean, you have to do something about those sigmas which happen with low probability versus those which high probability, but you can take care of that, and you get that you can take linear in the number of n and exponential in k, which is the alphabet size. And the exponent is d plus 1. D is the maximum degree. Okay, and then you get this guarantee that the KL divergence between P and Q is at most epsilon with high probability, and this sample complexity is nearly optimal. What about if there's confounding? So if there's confounding, then okay. So with arbitrary confounding, like I said, I mean, you can just have like an arbitrary distribution on n variables, and you can't do anything. So we can use this notion of C component, which was introduced by Jim. So there you have so you define a C component as a connected component through dash start. So for example, here X, Z2, Z3, and Y form one C component. Okay, and essentially for this problem, it's quite easy. You can so you can think of X, Z2, Z3, and Y as just kind of one block of variables, for which we don't know, for which there's no Bayesian structure. And then you can simply increase the degree by a factor which depends on the size of the C component. Okay, so if you assume that each C component has bounded size, then you can get a similar bound for the sample complexity of learning the distribution. Okay, another interesting question is, how do you learn a distribution on a subset, right?
So
yeah.
even for the confounding
Yeah.
phase, so you're outputting a description of what? I mean, of just the distribution, but you might be able to approximate things like, you know, the due distribution or other kinds of things.
Yeah, so we'll talk about that.
Okay.
So, right. So this is just a description of the observational distribution on these n variables, but really we want to get to interventional distribution. Okay. Yeah. Before I go to that, I mean, let me just also ask another natural question, where you don't want to learn a distribution on the whole set of n variables, but you only want to learn a description of a distribution on a subset, right? This is again a basic question. So yeah, so what do we really mean by a description? So there are two ways that you can think of what it means to learn a distribution, right? So one is you output the learning algorithm, if it's outputting Q, it outputs a box which is a sampler for Q. So you press a button and you get a variable which is distributed according to Q. Another possibility is that you get an evaluator which evaluates the probability mass function. So you input Z into the evaluator and you get as output Q of Z. Okay. So these are two different ways that you can describe a distribution. So learning a sampler is easy for the marginal. Basically, you can, easy in the sense that we have algorithms which are linear time in the size of the whole network. Basically, you just learn Q0 on all the variables, and then you throw away the variables you don't care about, and you get the variables on S. Learning an evaluator is actually hard. So we can show that it's hard for this complexity class SZK. A complete class is the graph isomorphism problem. So it's at least as hard as that. Okay. Okay. So finally, let's go to the interventional question, where you have a diagram with confounding present, and you get access to observations, and you would like again a description of a distribution that approximates the interventional distribution. So again, I'm satisfied with any description that is either as an evaluator or as a sampler. Okay. Right. So okay. So first of all, there's this basic identifiability issue that for certain kinds of diagrams, even infinitely many samples from the observational distribution does not yield enough information about the interventional, right? And let's just go through a quick example just to make sure that we are all on the same page. So here is the example that I drew on the board earlier, where you have x1 equal to u1 and x2 equal to x1 XOR u1. So in the observational distribution, x2 is 0 with probability 1. And you can just look at another distribution where x2 is really 0 with probability 1. There's no way to distinguish between the two using observations, but of course the interventional distributions are different, right? On the other hand, there are diagrams where you can actually find the interventional distribution. This is the classic front door example. So for any causal model on this diagram, you have this formula which expresses the interventional distribution in terms of the observational distribution, right? I say any, there's a slight catch in this. These conditional probabilities need to be defined. So as long as the conditional probabilities are defined, this gives you a way to express the interventional distribution as a function of the observational probabilities. Okay. So the question is, right, and Jin and Judea Pearl and Schwitzer and Pearl, they exactly characterize the causal diagrams for which interventional distributions are identifiable and not identifiable from observations. So for simplicity, let's just look at the atomic intervention case where you're intervening on just one variable. So their characterization was that it's identifiable if and only if no child of x is in the same C component as x. So for example, in this diagram, there's one child of x, Z1. It's not in the same C component as x. So the C component of x is Z2, Y, and Z3. So Z1 is not there. So here it is actually, so the intervention on x is actually identifiable from observations. Okay. Right. So our result basically strengthens this. So to say that if you have, if the identifiability condition, of course, needs to be satisfied in order to anything, you also need a positivity assumption. Just like I said, even there you needed a positivity assumptions on the conditional. So here I need to assume that so S1 is the C component which contains the variable you are intervening, and you also look at the parents of the C component. So if those, so any assignment to these variables occurs with probability at least alpha. So I assume that S1 is a bounded size set. So I assume that the C components are bounded. So this is a statement about a bounded size set. And I also assume that this in degree is at most D, and like I said, the C components are bounded by K. Then you can learn the interventional distribution both as this should be evaluator or sampler using again something like n times epsilon to the minus 2 times this alpha to the minus K blow up, okay, where alpha is this positivity parameter. And yeah, so in a conference next week, we present a paper which generalizes this to larger interventions. Let me just quickly tell you why this works. Basically, the way this works is that so like I said, I mean, you can remove these dashed edges by blowing up the in degree by a factor proportional to k. So k is the size of the C component. And then you can reduce. So the point is that the interventional distribution actually turns out to be the marginal of a Bayes net. Okay, so it's the marginal of the observational distribution on a different Bayes net. Okay, so you can come up with another Bayes net D. Okay, which is, I mean, the diagram of D is built using this diagram of P. So in the interest of time, let me not go into it. And then, so it suffices to learn the observational distribution of this new Bayes net D, okay, using samples from P, right? And this is where you get this alpha to the minus k overhead, because you need to generate samples from D using samples from P. And after that, you just apply a fixed structure learning algorithm to learn D, and you marginalize out X. Okay, right. So yeah, let me just point out some interesting questions. So yeah, it would be good to get kind of non-parametric generalization for continuous variables for this question. Also, another very interesting question is robust learning. So in the statistics literature in econometrics, people talk about double robustness or multiple robustness, where you basically have you have errors in the regression for different parts of this estimate, and the overall error depends only on the minimum error instead of the maximum error. So can we get something like this, or can we get I mean, yeah, robust learning kind of in the Huber sense? All right, so let me just conclude. So I showed you, I mean, finite sample pack style bounds for distribution and causal learning problems. And hopefully, I mean, you see the plethora of open problems that still abound, particularly, yeah, I mean, those problems that I mentioned at the end. Yeah, so one question that I'm trying to address is, I mean, like how to understand the tools from econometrics and potential outcome theory. How do they fit into the picture I have described? I mean, can I get pack style bounds from the semi-parametric estimators that people use in these fields? And also, I mean, what I talked about is counterfactual learning, is interventional learning. So I think Caroline Uller in a talk a couple of weeks ago made a good point that, I mean, there's this distinction between interventional learning and counterfactual learning. And in many of the applications, particularly in biology, interventional learning is actually enough because you want to predict the result of some treatment. But there are other situations where, I mean, you really want to understand counterfactuals. I mean, what would have happened if something else had happened? And yeah, so it would be also interesting to put those kinds of questions into this kind of pack framework. Okay, so that's it.
Thanks very much for the talk.
Yeah.
I have a quick question about the final result you gave was about sampling from or evaluating Q.
So it's both sampler and evaluator.
So can you say what the connection is between that and an estimator that achieves that bound? So if I wanted to now have an estimator to achieve that.
Right. So once you have a sampler for the distribution, you can use that to estimate expectations or other particular statistical quantities. Right? So you're getting samples from the interventional distribution, and you can use those samples to estimate the quantity of your interest.
And so I only need this number of samples such that the final estimate constructed from the empirical estimate constructed for those samples would be epsilon away.
Right. So what this guarantees is that the total distribution is epsilon away in total variation distance. So any statistic about a marginal, I mean, if you have a bounded statistic about a marginal of the interventional distribution, you also have a guarantee on that.
Thank you.
Yeah.
Just to clarify the left-hand red blazing star, what exactly are you?
Right. So here, I mean, this result is for variables which are discrete. I mean, they are on alphabet size k. But so typically, often when one looks at causal models, you have continuous variables, and you'd like to put kind of infinite dimensional I mean, instead of instead of saying that these variables come from some finite dimensional space, you'd like to kind of say that these variables come from some large family which may be infinite dimensional, and if one can get efficient algorithms for learning the distribution in that sense, I think that would be quite interesting.
I just more, I mean, you say non-parametric, so you want to get a wire stress type of, transportation cost type of estimate.
Right. Yeah, exactly.
Any other questions?
Right at the beginning in your first problem, you were comparing two distributions and you knew the model, right?
Right.
So why use total variation distance there? So somehow from the causal perspective, what I would really care about is that what sort of causal effects are different.
Right.
So what's
So,
the motivation for that?
Right. I mean, yeah. I mean, so you can generate the. So if you have a description of the causal model, you can also have a description of the interventional distribution, right? I mean, it's easy to get the description just by substituting values for some of the variables. And you could also ask the same question for the interventional distribution. But this was a kind of a general problem where you have a distribution on n variables. Right, so it makes sense when the distribution is on a high dimensional space. But if it's only an estimate about a marginal, then of course, I mean, that is quite easy.
But why worry about the graphs then in the first place? Why not just focus on the distributions?
Right. We are focusing on the distribution, but the graph is a way to regularize the distribution. So we are saying that the distribution is simple in the sense that it can be generated by a Bayesian, by a sparse Bayesian. Right. So the question is about the distribution. Right. Yeah.
I guess I'm wondering is that if I'm a causal modeler,
Right.
what I care about is the difference in causal effects.
Right.
And since I know that distributions can look very similar even for very different underlying graphs,
Right.
then it seems like the distance metric that I should be using to compare the two models for which I have so much information should not be just looking at the observational distribution.
Right. So this is for the observational, but I mean, if there's a particular interventional distribution you care about, right? I mean, you can write a description of that interventional distribution and apply the same result.
Hey, let's thank Arnab again. We're gonna coffee break now, come back here at 10:40 for Leonard's talk.